right. Good afternoon, everyone. Thank you for joining us this evening in this webinar organized by the Society of Spanish Researchers in South Africa and the Embassy of Spain in Pretoria. I am Maria Fabregas, co-founder of the Society of Researchers in South Africa, and I will be hosting this webinar this afternoon. So this webinar is the 5th one we organized since we launched the association in December last year, and you can watch all of the webinars in our YouTube channel, ACE South Africa. So today, our invited speaker is Alba Gomez Arias. Alba is a PhD candidate in the Institute of Groundwater Studies, University of the Free State in South Africa, and the Department of Earth Sciences in the University of Huelva, Spain. However, before Alba shares her work with us, I would like to introduce Dr. Bernard Rey, who's the head of cooperation of the European Union in South Africa, and will be telling us a little bit about the collaboration between Europe and South Africa, particularly the Horizon 2020 program, if I'm not mistaken. So Dr. Rey, whenever you're ready.
Can you hear me now?
We can hear you now, fantastic. Welcome, Dr. Rey.
It's really a pleasure to share the opening of this webinar with the Ambassador of Spain, Carlos Fernandez Arias. This session is a fantastic illustration of the meaning of Team Europe for South Africa, aggregating the EU, its member states, in all its diversity. And looking back at the invitation, more than 10 partners are represented. The embassy, the association, the university, and the European Union, of course, through Horizon 2020. And all of them play a role. Of course, the hard work has been done by Alba and her research colleagues, but still there is some association. But it's more generally the illustration of the importance and the special role played by scientific cooperation between EU and its member states and South Africa. And there I come back to my position of head of cooperation, a science that contributes to this common and global agenda, the sustainable agenda, and the SDGs. And in this context, water is critical for sustainable development. Access to fresh water is an important element to access many of the sustainable development goals. If you do not have clean fresh water, it's the fight against poverty, hunger, provision of primary health care, clean energy, which is affected. And on the contrary, too much water, like you have floods, hurricanes, is also a hazard which affects the lives of vulnerable communities. So research and innovation play an important role in protecting and ensuring an efficient use of water, including through circular approaches. And a strong scientific and technological base is needed to develop appropriate and innovative solutions and tools, which will ensure sufficient access to water, particularly in Africa. So it's not a surprise that water has been an important area of activity in the successive European research and development framework programs over the last decades. In 2015, the European Union launched 2 dedicated Horizon 2020 calls to address water-related challenges in Africa. Water 5B 2015, horrible names by my research of TGRTD, but you will not give my name if I say it. A coordinated platform, and another program, Water 5C, development of water supply and sanitation technology and our methodologies. And South African researchers have participated in several projects funded under these calls. If I have the name, Afri Alliance, Safe Water Africa, Water Sport. Funding from other Horizon 2020 calls was also available for water. The project, the Research and Innovation Program on Raw Material, ERAMIN to foster circular economy has been financing the BDAS system, which was implemented in Huelva and now soon tested in Wales. But more recently, a huge call has been launched by DGRTD in September, a 1 billion Green Deal call. And it really aims to foster innovation to accelerate a just and a sustainable transition to a climate neutral Europe by 2050. And it includes resource efficiency, water, and other type of pollutions. So looking to the future, because of course this is always what is interesting, water-related activities within the new program, Horizon Europe, which replaced Horizon 2020, will definitely support the objectives of the European Green Deal, a paramount importance for us. It's related to climate change, climate action, farm to fork strategy, the EU biodiversity strategy, the circular economy action plan, the ambitions for zero pollution, and the industrial strategy for Europe. And in particular for water, a European partnership called Water for All, Water Security for the Planet, is currently being developed. And the objective of this Water for All partnership are to provide solutions to the current and increasingly important future water crisis. Water scarcity, increasing demand, pollution, extreme events, and to increase the impact of public and private research and development funding through joint planning and implementation. And we encourage European and South African partners to keep working together and to engage with us in the development of this initiative. So keep your eyes open for more on Water for All, other initiatives, and looking forward to participate in more of these events, which really show the importance of European Union in South Africa. Thank you.
Thank you very much, Bernard, for this introduction. What a beautiful name for a program, Water for All. Thank you for putting Alba's project into a framework that it's actually not just, this is just a grain of sand in a much bigger project. So thank you for this introduction. And now we're gonna, I don't know, Bernard, will you stay till the end for questions and answers, or you might not be able to stay?
I may not be able to stay the whole period because there is something in between. I listen at the beginning, but I may not be able to stay the whole period. That's
fine, no problem.
Thank you.
So we're going to, thank you, Bernard. We're gonna hear now the introduction by the ambassador of Spain in Pretoria, Mr. Carlos Enrique Fernández Arias, who would like to introduce our speaker, Alba, and her work. So let me share my screen with all of you. And we can listen to the words that the ambassador has to say.
Good afternoon, and welcome to our second series of webinars organized by the Embassy of Spain in Pretoria and the Society of Spanish Researchers in South Africa. As the previous one, the aim of this second series is to raise awareness of the efforts of the about 50 Spanish scientists who currently live and work in South Africa, as well as illustrate some of the results of the research work. Today's webinar is offered by Ms. Alba Gomez Arias, doctoral researcher in environmental geology at the Institute of Groundwater Studies in the University of the Free State. Together with other researchers, Ms. Gomez has developed in South Africa a water treatment system named BDAS that can be used worldwide to treat from acid to alkaline water produced by mines and other industries. It is a great improvement of a system used in Spain to treat acid mine drainage, which has been tested in both countries thanks to a project founded by ERAMIN in the Horizon 2020. In South Africa, it has been developed on a pilot scale at several mines in the country, and the first full-scale project is still ongoing. The synergy between Spain and South Africa in the core is the cornerstone of this system, recently patented internationally. I hope you enjoyed. Thank you very much.
All right. Let's see. Wait. I can't now. There you go. Okay. Well, great introduction by the ambassador. I probably don't have much more to add. So let's not linger anymore and start with Alba's presentation. Before that, though, I would like to remind you all that if you have any questions, you can type them in the chat box and during the webinar, and we'll address them to Alba once she's done. So please feel free to, whenever you have a question, just type it there, and at the end of the webinar, Alba will address the questions. So yeah, let's not delay this anymore. Alba, please go ahead with your presentation whenever you're ready.
Thank you very much. Yes, I'm gonna share the screen here. There we go. Okay. First, thanks for the opportunity to be here in this webinar, and thanks for the invitation. Thanks for the great introduction of the ambassador and the minister. So first, thanks Bernard a lot for your introduction. First of all, I want to say that this is actually a team's work. So I'm here in representation of all the people who made it possible. Obviously, I didn't create the BDAS myself. The BDAS is BDAS because that's Spanish for life. So we thought it was a nice name for it. And it was a big team who helped throughout the process, from the creation, the invention, the in practice, and finally to make it. Before I explain to you what is the BDAS system, I want you to know what is actually that we clean, which kind of water we clean, for all of you that are not familiarized with water mine and so on. So basically the system was designed to treat acid and alkaline mine drainage, and eventually we also treat industrial acid drainage. The mine drainage basically is produced by the barite that are in most of the waste rock dams and the tailings of the mines, and they acidify the water with when it's in contact with the water. It liberates iron, sulfate, and proton. That is the cause of the acidification. And the main characteristic of the acid mine drainage is that it's very high in metals. However, sometimes you have very alkaline rocks that can neutralize that acidity, and then you will have a non-acid mine drainage, which is basically this alkaline mine drainage that is characterized by a high pH, a low metal concentration, but high in salinity. Normally, it's a very hard water with high anion. So the BDAS system, it's a modification of the DAS system. It was in 2012 when I personally get to know the DAS system. I was doing my master degree in the University of Alba, and they started speaking about many passive systems, and one that they were working on, it was the DAS system. That was a system that was implemented to treat in a passive way acid mine drainage. They basically use limestone or magnesium oxide in a fine grain particle size, and they mix that with good chips. By mixing the reagent with the good chip, they create a big space, they increase the porosity, and then they avoid the clogging problem, because most of the passive system, they have that problem. They very soon get clogged. So the system gets decreased the effectivity of the system. So in 2013, I moved to South Africa, and I found out that actually here, most of the mines, they produce non-acid mine drainage. So if I want to help South African mine drainage, I can't use that system as it is. We need to change the system, and we need to create a new system. So basically what we thought, it was to use barium carbonate as a reagent in a DAS system. So we keep the idea of using the good chips, but in place of using now as a reagent limestone, calcite, or magnesium oxide, we use now barium carbonate, and we use it in powder. So we increase the porosity even more, and basically what we do with this is that a treatment that can clean acid and alkaline mine drainage. Basically, this system can remove 80 to 95%, even up to 100% in some case of sulfate. It also reduces the hardness, the salinity, and so on. So basically how it works is I have barium carbonate here in red, and the water will come with sulfate, and it will have some cations of calcium. So the barium will react with the sulfate, and it will precipitate as barium sulfate, while the carbonate will react with calcium, magnesium, and some others, and it will precipitate as a calcite, okay, as a calcium carbonate. So we start doing some batch experiments at first to see if our concept will work, and we actually have pretty good results. I don't know if you are looking at this, okay. So basically, when we treat semi-neutral to alkaline mine drainage, we could see that we improved the pH was increasing up to 7, from 4 to 7. But if we are already in pH 6, that water will get even up to pH 10. So then all the sulfates were removed to drinkability, and all the metals, D and 3-valent metals, they actually were removed almost at 100%. So we again are in drinking water. With the TDS, conductivity, all the salinity, we actually decrease it up to 50%, which is not bad. It's actually the first passive system that can achieve that. So then we start doing our lab scale system. We basically use these columns here. One of them we're treating a more acidic mine drainage, and the other one was an alkaline mine drainage. And the results that we got, it was even better than in the batch experiment. So the pH were increased, again, the TDS decreased, the conductivity, the sulfates were 100% removed. There was no sulfate at the outlet from the first week that we started sampling. This was, experiments were running for 26 weeks. But while we were busy doing all of this, something happened. It was beginning of 2014, while everybody was still in Christmas holidays, and there was a peak of rain like it was never before in the past 100 years. It was something very big and very unexpected. So in Palaborwa, there is an industrial complex. You see here very little. All of this is the Kruger Park. Here is Palaborwa, the town. Here is an industrial complex called Palaborwa Industrial Complex. And there is a fertilizer industry. There is an industry there that produces phosphoric acid. And, produce phosphoric acid. And what happened there is that because of the rain, this wall couldn't handle it. And the water started having some spillage to the dam nearby. And from there, it got to the river. So then it was all over the news, the fish dead in the Kruger Park and so on. So we ran to the lab, we got samples from there, we ran to the lab, we started doing all the batch experiments, we make column experiments by like in 3 weeks in place of 3 months. We already got enough results to know that the system may work. We made some changes. So basically this is the system that we implemented on the site. We took the water. It was at pH 2.5 at that time because it was mixed with the water in the dam. And then we start having a reservoir tank where we produce some oxidation. Then the water will go to a calcite dust. This is the one that where I was taught when I was doing my master. And then we implemented the BDAS tank with the barium carbonate here. And from there it will go to decanter, where later on we discovered that some microbial interaction were playing a big role here. And from there it would go to a cascade, okay? So just in detail, the water will go to a sand filter because we use a pump and we don't want the pump to be blocked by any. Then the water will have here, there will be a turbulence flow. It will make like a cascade because the water was actually around here. So we promote some iron precipitation here. And then the water will go to the next tank, that is the calcite tank, where most of the trivalent metals were precipitating here. We increase the pH a little bit, up to 6, 7, and then the water will go to the barium carbonate. This BDAS tank will remove all the divalent metals and the trivalent metal that were remaining there. The pH increased more, and then the sulfates were also removed thanks to here. And when we, with this scheme, here is what happened in the last step, that is we found out some biofilm there, and when we analyzed, we saw a lot of aragonite and calcite growing there, and they actually were precipitating a lot of salts. This is another study that we're starting to work right now, actually. And this was the first plant that we built for the BDAS. So basically what we had there was amazing results. We didn't believe that we could get such a good quality of water. So if you see the pH, it's in this line here in red, increased from 2 all the way to 7. The phosphate that was in the water, it was 8,000 ppms. And at the end, we were below detection limit. The same happened with the sulfate. From 4,000 ppms, we were barely 1,000 ppms. And that is an average. We actually get at some point 400, 200 ppms of sulfate and things like this. Also the conductivity, TDS, and it was removed 64%. So as you see here, most of the metal were almost completely removed. And it was a very high concentration at first. So this was a remarkable achievement. So when we, thanks to this, that we could actually help the site to clean the water, and then we were at some point, and then we decided to give it a chance to this idea, and we start doing the patent process. So basically in 2014, at the end of the year, we start our national application. Then on the 2015, we started the international application, and it was actually in 2018 that we finally got the international application granted. And obviously previously was the national. So I want to acknowledge the inventors. First, it was Esteban Herder. She was at that point the leader of our group and the one that make everything possible. Julio is the person who came with the idea, so everything is actually thanks to him. I was helping since the very beginning. I designed the first pilot plant, and this my PhD. And then Ruan and Walid, both of them worked, one in the lab and the other, all the pilot plants built here in South Africa. He actually make it possible. Thanks, Walid. So here you have some examples of how the pilot plant looked like. So we have here some reservoir tanks. In this case, it was the pilot plant that we built for Exarro. It was an alkaline mine drainage, so we did not need the BDAS, the calcite dust system. It was only with the BDAS, and then the water will go to a decanter, and here is the cascade. We were treating 8.5 cubic meters a day, and we actually achieved drinking water quality in this case. For Eskom mine, it was alkaline, but it was more neutral. Not that much alkaline. We reached drinking water quality. It was the same flow rate, but we couldn't deal very good with chloride and sodium. So the salinity, the taste was not all that good yet. The last one that we did, this one I was pretty much involved in, it was in the 4 South 32 mine. This one, it was an acid mine drainage. So in this case, we did at the calcite dust system. It was this rectangular, this rectangular tank. And then the water will go to the barium carbonate here. And from there to go to the decanters and the cascade. This one, we increased the flow rate. It was 10 cubic meters a day. We did reach drinking water for most of the parameters, but sometimes we struggle with the barium to keep the concentration of barium below the limit, and sometimes also with the manganese. Sorry. So now you will think, okay, this is a water treatment, it works very well, but it is not profitable yet. So how did you make it profitable? Basically, for this, I want to start speaking what are rare earth elements. Here in the periodic table, you can see all the lanthanides are considered rare earth elements. And in that group, most of the time, they include also the yttrium and scandium. And these are called the rare earth elements, not only because they are rare, it's also because it's very weird that you find high concentration of them, like minimal concentration. And they are also included in the critical raw materials list, which means they are very valuable and we need them. Like they are in all your cell phones, in the electric cars, in tablets, and everything. So it was in 2017 when we were invited by Prof. Carlos Ayora to participate in a project called AMDRE. It was a proposal that we submitted to the ERAMIN call of the Horizon 2020, and it was about this, about to extract rare earth elements from acid mine drainage. Okay, it was a collaboration between Huelva University, Barcelona, here in South Africa at the University of the Free State, and it was a very big team of very, very talented people. So here you have one of the meetings that we did at the end to share all of achievements and expose all our results to the funders. Here it was the DST in total in the middle. So basically, the outputs of the BDAS project, it was first, thanks to the BDAS project and the collaboration that we started between the University of the Free State and Spain, BDAS was tested in Spain. So at first they were doing in Barcelona and in Huelva some lab scale experiments, but at some point they even include the BDAS system in their pilot in full scale. Then also the BDAS was first published between the CSIC, the University of Huelva and the University of the Free State. And what is most important for me is that I started my joint PhD. I started a degree between the University of the Free State and the University of the Huelva. It was sponsored by this project. And you remember Palaborba, right? This place is where we put our first and in a hurry pilot plan to see if we can help this little industry here to deal with the acid water, okay? So this is the fertilizer industry here in red, and they produce phosphoric acid. So the byproduct that they have is the phosphogypsum stacks here, and all of this black that you see is the dams where they collect the drainage from the phosphogypsum, and also where they have all the wastewater from the plant. And all the rest here in yellow is the Palabora Industrial Complex. So here we have in orange a company that produces copper. They basically extract copper out of this open pit. Now they went underground mine, and they extract copper out of carbonatites, which is very alkaline rock. And then this company here, this is a mine that extracts phosphate rock. They extract phosphate out of the phosphorite, which is also an alkaline rock. And these ones sell the phosphate to them, and they produce the phosphoric acid, okay? So then I thought, the system worked very well, but what if we can make it a profitable system? What if we can extract rare earth out of the waste that we know it's here, and out of the water that we know it has rare earth elements because it comes from the same rock, right? And what if we make it cheaper? Because actually this water here has 52,000 ppm of net acidity. So it was very acid, and it consumed the limestone that we put in the first tank, it's super fast. So this way we may be able to make a cheap and even profitable water treatment. But to do that, we need to change the model of the business model. So normally a mine will dig, will process, will extract the copper, iron, phosphorus, everything that they need to get, and then they will dump the rest in the waste rock dump and in the tailings. So what if we change the model to a circular model? In this case, we will take the waste, and we know it's enriched in rare earth elements. We can use it to process and clean the water, and then you will get an enriched byproduct that you can process and extract your rare earth elements. So to do that, first I need to demonstrate that there is rare earth elements in the waste, and the rare earth elements concentration is good enough for this to be really feasible. So I did analyze all the waste rock dumps, all the east tailings, and thanks to the University of Alba, we could do all the mineralogical analysis here. And we got that 0.17% of the waste rock dumps, it was rare earth elements oxide, which is not bad at all. We also analyzed two tailings. The one it's called east tailing is the tailing from the copper mine, and the Selati tailing is from the phosphoric mine. And they have 0.15 and 0.11 percentage weight of rare earth oxides. So now that I know we have rare earth elements there, I need to know if actually this rock has the neutralization potential that is needed in order to neutralize the acidity of the drainage from the phosphogypsum. So what of them all, actually the carbonatites and some of the samples of the east tailing, some of the sections of the tailing from the copper mine, it was very high. It has very high neutralization potential. So yes, it could work. Then we need to know, okay, I can use this waste to treat the water, but what is going to release? I need to know that I'm not going to release any toxic elements to the water because I want to clean it. I don't want to make it worse. So then I did some total component analysis and some leachate concentration analysis, and I compared this with the South African threshold, this TCT threshold and LCT thresholds, and according to South African and international regulations, the solid waste from the industrial Palabora complex, it is not toxic, which means it won't release any toxic elements above the limit that is considered as a toxic, okay? But this is not really enough because basically South Africa used the very same toxicity test for every kind of waste. So it's not specifically for mine waste. So I decided to do a BCR, sequential extraction, which is the graphic that you have here. Please note that this is not the same than this one, which means the tailing is actually way lower than some of the rocks. And what we basically saw is that, okay, I'm not interested in use the pyroxenite because it has more concentration of elements that can be toxic, and because they have very little to non-neutralization potential. So I want to focus on the carbonatates and even better, the tailings. So if you see, the east tailing is the one that had the highest neutralization potential, and basically what it has is going to be 30 milligrams per liter of sulfur. We already know that the barium carbonate can deal with the sulfate very good, so that's going to be a concern. Then there will be 5 milligrams per liter that can be released of manganese, which is not so much, and then you have some copper as well, and then you have a bit of barium. We already put barium in the system, so any of those things were a concern, which means let's go ahead and let's start with the water treatment experiments. We ran some models first, and we saw that because our tailing, we decided to go for the tailing because it was, according to all the previous results, it was the more suitable one. And it has calcite, dolomite, and fluorapatite, and we could see that they are in the saturation index below 0, which means the water that we are going to treat, it will dissolve these compounds, these minerals. that are in the tailing. And while they're doing that, the pH may increase up to 4. Okay, so then when we run the batch experiments, these ones here, we could prove that actually the water did reach pH 4 and the conductivity and TDS decreased, not much, maybe at 40%, but still for a first step of the water treatment, it was already very good. So we decided to go for the bench scale experiments. So we have the acid wastewater from the phosphoric acid industry. We pump it to the first reactor, which it was filled with the tailing mixed with the good chips. Here, the water will be treated as it goes down gravitationally, and then we pump it again up to the next reactor, which it was a BDAS reactor, one reactor with the barium carbonate mixed with the good chips. And then it will go down and it will get out as clean as it can. Let's see how clean it gets. Well, at the inlet, we were using the water, the pure water, not the one that we were cleaning at the dam, but the original one that had pH 1. And we actually could achieve a pH even 6, which is not bad for a passive treatment using cheap or free material. And speaking obviously about the first step. Also the conductivity and the TDS and salinity, it was decreased quite a lot. It was above the 50% in this case. Then the rocks, this tailing has phosphates, sulfates, fluorides, calcium, magnesium, nickel. All of these are compounds that they were in the tailing. So obviously, if we put acid drainage that it will dissolve the calcite, it's going to release calcium. It's going to release carbonate, it's going to release phosphate because it's in the rock there from the fluorapatites. It's going to release all of this. So we saw an increasing on phosphorus and sulfates and fluoride, okay? But all of them were removed by the BDAS later on. So if you see, we get to 0, close to 0, at the outlet of the system. And with the fluoride, it was the same. Only with the phosphate, we still have something remaining in the water treatment. Calcite was also well removed, but as the time moves on, the system effectiveness was depleted. So we finally got at the outlet 500 ppm of calcite, but at the beginning it was just 0. So this, we just leave the experiment running until the system was completely depleted. However, with aluminum, chromium, iron, it worked perfectly, and it kept removing 100% of all of them all the way till the end of the experiment. So even when the system, the reagents were almost exhausted, we still have no heavy metals coming out of the system. And what is very important, the rare earth elements. What we thought was very interesting, okay? You see, this is the inlet. This is the water I'm putting, and I have between 6 and 8 milligrams per liter of rare earth elements in that drainage. But when it gets in contact with the water, just in port 1, okay, there is an increase, which means, let's move to the column, when the water gets in contact with the tailing, it starts dissolving the calcite, the fluorapatite, and that make the rare earth elements to be released to the water, okay? So I'm removing part of the rare earth elements from the top, and they all precipitate, if you see here, they all precipitate at port 2. So from here onwards, there is no more rare earth elements, or almost no rare earth elements in solution, which means we might be concentrating all the rare earth elements just in this section. And what happened with the uranium? And normally, uranium and rare earth elements, they are precipitated together. So we were expecting that we, like everyone else, are removing rare earth elements, and that would be together with uranium. But here, we didn't see that. We saw that the uranium keeps up and down, and even at the outlet, we still have quite a high concentration of uranium in the water. Where is the uranium going? Port B1. As soon as this water enriched in uranium gets to the BDAS system, all the uranium is out of the water and it precipitates here, okay? Which means we're having perhaps an enriched rare earth element substrate depleted in radionuclides. So we want to know if that is true. When we finish the experiment, we open both columns. Actually, this one is a picture of the BDAS column, but we did the same with the other one, okay? So we open the columns, here you see with a good shaving, and we took samples from the top, middle, bottom, okay, all the way down. This is column A and column B. So we saw that the rare earth elements, as you see, concentration of rare earth element original from the tailing, and it was depleted a little bit, which means this is the amount of rare earth elements that was contained in the calcite, dolomite, and fluorapatite mostly, and it was released. And then they start precipitating downwards in port 2 and port 3 and downwards, okay? And we see that there's a little bit of rare earth elements that still reach column B, which is the BDAS reactor, okay? And what happened with the uranium? All the opposite. We don't see really much enrichment of uranium in the first reactor, but we see that it got precipitated in the column B with the barium carbonate. And where did the rare earth elements go? Well, we found all around the column A, full of newly formed phosphate. All the newly formed phosphate that we found, it was just these ground masses that were around the previous tailing mineral particles. So here you can see a calcite that it has been almost completely dissolved by the acid wastewater, and surrounding started precipitating this new phosphate, okay? When we analyze the phosphate concentration with EDS all around in the samples, we found that it was enriched in rare earth elements, lanthanum, cerium, neodymium, all of them. So we could achieve the following. First, we know that the mine waste has quite of rare earth abundance there. We know that the rare earth concentration in the acid wastewater is also high because actually it comes from a plant that has been processing those materials. We know that the mine waste has neutralization capacity, so we may be able to use it to neutralize the acid water. And we know that the toxicity of the leachate that we want to use, the mine waste that we want to use, they are not toxic. And when we do the water treatment, we could prove that the water quality improved a lot. Not drinkable quality, but we come from pH 1, don't expect that, but improved a lot. And then the rare earth accumulated, it was accumulated in the reactor A and in a very particular section, which means all your rare earths are there. You can take it out and perhaps sell it. And we found what it is. It is in a newly formed rare earth rich phosphate. If all of them is in a rare earth phosphate, it's very easy for a plant to process that substrate and extract rare earth elements. But now we need to keep going with the marketable byproduct, if it's really profitable, if it can really go to be sold. And so far, all we know is if you treat all the water that is in the fertilizer industry with all the tailing that they have, just using the Cooper tailing, you may get a concentrate byproduct that is worth $60 billion, according to all the rare earths that are in the tailing and that can be concentrated to be more feasible to work with that material to produce the rare earth oxides. So that is done. But we still need to, calculate the revenue by deducting the capex, the opex, and finding out how the process will be further. And with that, I want to thank everybody, the inventors of the BDAS, everybody who participated and helped to develop the system, particularly the AMDREI participants, of course, the DST for the funding through the AMDREI project with the Horizon 2020, the TIA that was starting there when we started doing the studies with the BDAS. They were funding the Extreme Biochemistry group back then. And now they are still helping us through the environmental microbiology group to determine what are actually the bugs doing in the last step of the BDAS system, removing the salt. I want to thank ACE, South Africa, for this opportunity, organizing this webinar for us, and also to the Embassy of Spain for sponsoring the webinar. Thank you very much.
Thank you very much, Alba. That was a really interesting talk with a lot of vision. Let's see if there's any questions here in the chat. Remember, attendants, that you can, if you have any question for Alba, you can just write them down in the chat box, so we can ask Alba. But in the meantime, don't be shy. You can ask, but in the meantime, I would like to ask you, Alba, what are the future steps planned for this research?
Well, now we are more deep going into the microbiological side of this thing. Since the very first pilot plant that we put, we found out that some biofilm were growing in many steps. Particularly in the barium carbonate tank. The thing is, the reaction that happened in that barium carbonate tanks is quite oxygen consuming. So we are creating a near zero oxygen environment, which is wonderful for the bugs to grow. So we knew that by chance we were making a paradise for the bugs. We didn't really look into it. We didn't want them to be there, and we didn't expect them to have a play in this system, but it does have, particularly in the decanter. So the decanter is an empty tank where we just expect that whatever was in suspension, it will decant and we get out the clean water. And so there is nothing there. But when the water comes in and it has still some salinity in there, we said that the main issue it was the salinity, that we remove just 60, 70, 50%. But when it comes out, it has less salinity. And then we have, in between, we only have an empty place with bugs. So now there is ongoing research about what are the role of these bugs. How are the bugs using the salinity to to eat from them, to feed from them, and how are they helping to precipitate those salts at the bottom of the tank, and then how we can improve this that is happening, and perhaps we can go further in implementing in a maybe desalinization plant, like the ones that clean the water from the sea, and do a eco-friendly technology with bio bags, just helping with that. That is one thing. The other thing is we want to really be sure that the water treatment is profitable. So we know it has a lot of potential. The numbers are there. There is a lot of money that can be get out of there. Now, is there the technology to extract the rare earth elements from there? Is it profitable? So we need to do a feasibility study. Would it be profitable? I mean, I think so, because it is a passive system with very low capex and very low opex. The capital cost and the operational cost is very low. So out of $60 billion, I think we might be able to get profit. Not we, the mines. So, yeah.
Great, Alba. And that project that you're mentioning with the bacteria, it's still part of your PhD? No, that's a parallel study that they're conducting.
My PhD is done. I submitted my first draft to my supervisor.
Okay, so that's done.
No, this is another project that is starting recently now with TIA. It's the leader is Dr. Julio Castillo, and it's going through this environmental microbiology group.
Wow, I think it's fantastic. So not only you can make this profitable, but also the byproduct profitable.
Yes.
Maybe. So that's fantastic. Great, Alba, thank you. We have a question here from Manuel Caraballo. says, amazing work, congratulations, I agree. And he asks, I would like to know more about the cost of BaCO3 and the availability of this reagent to build a full-scale treatment. Could you give us some estimations?
Yes, the cost about the barium carbonate, it think per ton, it depends. It has changed a lot. The first time we bought it, I think it was $500 the ton. That we actually need very little if you compare, for instance, with the calcium carbonate. It depends of the amount of barium carbonate that you will use. It depends on the concentration of sulfate that has the water. So for instance, now we are working in a pilot plant to be built in Gales, and they had very little concentration of sulfate. So for the pilot plant that they want to use, I think 50 kilograms of barium carbonate is enough, while they're planning to buy like a ton of calcium carbonate. With 50 kilograms is more than enough to clean that little sulfate that they have in the water if they plan to use first the calcite tank and then the BDAS. I hope this answers your question, Manuel.
Manuel, if not, you can, if it's not clear enough, you
so
can,
it is
you
more
can ask
expensive.
again.
Yeah, it is more expensive than the calcium carbonate and the calcite and limestone because it's just limestone. I don't know if it's more expensive than the magnesium oxide. I don't think so, but I'm not sure. And yeah, that's what I can say.
Okay, thank you, Alba. Meanwhile, people are thinking about their questions. I have one more question for you. As someone who is completely unrelated to this field, but I was wondering, I'm assuming yes, but this is just an assumption. So are there other water treatment systems for mines in the world that are being currently implemented? And if so, how do they compare to this water treatment system?
Well, there is many water treatment systems. You have passive ones and you have active ones. Normally, if the mine is operative, they are using an active water treatment. Normally, they use reverse osmosis. Reverse osmosis works perfectly. You get to drinking water quality. And if you have a filter in your house, it's basically that technology, but at a huge scale. And then the problem is that it's very expensive. But you know, if the mine is running, they have profit enough to cover that system. The problem is that they create a lot of brine. This is a very saline water, and they produce like few times more liters of brine than the liters of water they are treating. So the waste of that system is a concern. So nowadays in South Africa, for instance, they are trying to move away from the reverse osmosis, and they are starting to look into more environmentally friendly way of cleaning water, because if you clean water but then you are making a mess on the side, then what is the point, right? And so this system is actually a passive or semi-passive system, because normally we have to use pumps to extract the water if we don't have the landscape favorable to do gravitational flow of the water. And normally these systems are used mostly for closed mines. So all the sites that you have seen, except the first one, that was the phosphoric acid industry, it was still working back then. The rest have been abandoned mines. Abandoned mines, I don't mean abandoned, I mean mines that have been closed already. And normally some of them, if they are recently closed, the company has still to deal with the environmental management of the closure. And one of these steps is going to be to be sure that they are not polluting the environment, they cover the dams, they clean the water and so on. And for that, they normally use passive systems like DAS, like wetlands. They use the natural wetlands they normally have to remediate, so they build wetlands to help remediating the water. There is ADL, there is a lot. I can speak another hour if you want to.
So how would this system compared to the others, as far as I understand, is that number one is very cheap, and number two, it can make profit out of the waste.
So yes, if in the case of Palabora, because we have quite a high concentration of rare earth elements, and that is a very valuable material, then you can not only defraught the cost, but perhaps if the numbers turns okay, you can even make it profitable, which means the mines, it's not that they will be like, I have to treat the water, I don't know it's costing. No, they will be like, let's treat the water, I want to get that money. So that was the main aim of my PhD. It was to create a system that no one would say, no, I'm sorry, I can't help the environment, it's too expensive, and if I'm not enforced to do by law, I won't do it. No, this time I want them to be keen on cleaning the water and getting revenue out of that. That's the first, but that won't happen everywhere. If you don't have rare earth elements, they can't come from nothing. Or if you have a lot of copper, then you can precipitate copper. If you have something that is valuable, if you have gold in your water, then we can try to precipitate gold. But basically, the main benefit, if you don't think about the revenue or the non-profitable, non-expensive place, one of the main things that there is no other that I know of, maybe there is, somebody can hear, correct me, that remove sulfate, like 100% of the sulfate. There is no other that does that. Also, they struggle to remove some of the divalent metals. Also, for instance, if you use calcite, like in the calcite dust, and you don't put the BDAS later on, you increase the calcium that is released. You know, you have calcium carbonate, and the calcium gets released in the carbonate to the water. The carbonate is good, but the calcium remains there, and it can cause hardness and salinity. So this system is all the way. It will capture the calcium and anything else that is in solution. So you will get that problem solved.
Well, Alba, I'm really impressed, honestly. I told you already yesterday, I find this fascinating. So congratulations on the work of your PhD, on the work of the whole project that you said is, as in most research, is teamwork. So this is a lot of people working to achieve a goal. So yeah, congratulations. There's no more questions. So I guess this is it then. Thank you, Alba, very much for the presentation. It was really a pleasure to have you here in these webinars. Thank you all the attendants for your attention and your time. And just remind you again that this webinar is being recorded, and you can watch it again or send the link to colleagues. It will be posted on our YouTube channel. So yeah, thank you everyone, and have a good evening.
Thank you. Thanks
Bye.
everyone. Bye.
Bye.
Thank everyone.